Welcome back. So earlier today, you heard about the mechanical portion, basically how do you put your vehicle together. Now I'm going to go through how you actually power the solar car. So we'll talk in this section about your array choices, power trackers, and then all the way down to your electric motor and controllers, and also batteries. So first off, your solar array. So, let's talk about how you get the energy into your car, and then we'll talk about how to use it. In terms of solar array, the very first thing you have to consider, sort of part of the mechanical side of things, is how do you support your array? You're going to have to look and say, based off the array that you choose, and we'll talk you through some of your choices, you have to look at and say, how do I integrate that into my solar car frame? You have to look at rigidity in terms of, if you have flexible cells and you have very little suspension, you have lots of rattle, that could introduce micro fractures into your solar cells. And if you've ever seen a bare solar cell and you put any amount of pressure on it, you'll just crack the solar cell. And so you have to be very careful, and you want to capture your array in a very rigid way. Cooling. You have to consider that essentially solar cells are electronic components in a sense. And so solar cells work better when they are cool. And so you'll see teams actually be cooling down their array to make them work more efficiently. The downside of that, of course, is if you cool down your array from a very hot temperature, you now introduced a very big temperature difference, and that could cause some microfracture. So you have to experiment and deal with that. Weight and connectivity. So weight, obviously, how you capture it. If you want a really rigid, frame for your array, that's going to be heavy. So you got to figure out and it's your trade-offs for that. And then connectivity. So when we built our car in '97, we built an aluminum wing, which is fairly conductive. But then we put this insulative layer on top of that, and then we mounted our solar cells on top of that. Well, if there were any type of break in that insulative layer, that would cause it to short onto that aluminum layer. And I'll say it happened. We were, at times during the competition, we were able to detect a voltage, to the framing where we captured it. So it's something to consider. We'll talk about what options you have to deal with that. So as I said, the solar cells' efficiency changes as their temperature changes, right? So the higher the temperature goes, the less efficient it is. So you really want to cool that down to get the most efficiency. Now, obviously, you're not going to be mounting misters on your solar array as you run, right? But considering your design, the idea of how you perform air cooling on your array to make sure that as your car moves, you can keep your array cool. Okay, now let's talk about the shape of your array. Lots of design choices there, right? And the most common design that we see is this whole wing over body design, where you have an absolutely flat array. Your driver sits underneath that array. There's benefit to that because you're actually shading the driver. But the best benefit is you maximize the amount of area that you have. Look at the car on the left. You see there's a canopy, but they lose that area where you can place solar cells, right? So you get better aerodynamics, so you use less energy, but you also get less energy input. So it's something to consider when you do your design trade-offs. Also, if you have a flat array, you don't have to worry about the angle of the sun. So if you have a more aerodynamic array and you put an arc in your design, the cells on the right half of your car may not be angled to the sun in the same angle as those on the left side of the car. And then you have to start considering, how do I make sure that those cells are not in the same series circuit as each other? Because if you wire all these solar cells in series together, it will operate at the lowest performance of any one cell. So if you were, for example, to shade a cell, then it would affect all the other cells in that chain, even if they're not shaded. We talked about curved arrays. So as we talked about, solar cells are very fragile. And so the more curve that you put into it, the more chance that you have of breakage. And then the more issues that you have in terms of the angle of the sun, as we just discussed. Now, why do people do this? It's really to match the aerodynamic shape. So again, it's that trade-off about, do you want more power, or do you want to design your car to use less power and be able to collect less power? I'll say that there are semi-flexible cells that are out there, semi-flexible panels, so there is some give you can introduce in your solar array. And so you just have to design it so that if you want that curvature, that you don't have some major changes in angle, or else you can cause breakage. But something like this, where it's a fairly gradual changes in angle, still works quite well. The options that you have in terms of actually buying the solar array. Most first-year teams might get something to the effect of these commercial panels that have these heavy frame around it that you might put on top of a rooftop. And those are really beneficial because they're meant to take snow, hail, thunderstorms and all that stuff. You don't have to worry about weather at all. It's very reliable. And because of the market of trying to put these solar panels on roofs, they're very easily purchased. But, a frame like that, we're talking about, 15, 20 pounds of a panel out there, right? That's fairly heavy compared to some of the other options that you have. So, you just have to consider this. The other thing you have to consider is a size. These tend to be fairly large in size, and you have to look at our regulations to see, can you fit enough of them inside your the area that you have. A lot of teams design this sort of split wing over body for these type of cells because it happens to be that the width of one of these panels are slightly over, so that you can only fit like 5 panels going forward to back, unless you do the split, and you might be able to fit a 6th one. So it's something to consider in terms of your design. These semi-flexible cells are a fairly new in the last 5 years, but fairly popular application for solar cars. Why? Because they get the benefits of the reliability of a commercial rooftop panel without the weight of the frame. You can basically have just this panel. It's already insulated for you, encapsulated, so it can take some amount of rain and things like that. But yet you can mount it to anything that you want. You can put it on a surface and just Velcro or even adhere it to a surface. And you can even get some type of aerodynamic gain out of that. The problem with these panels, however, there's always a pro and con, right? The problem with these panels is you see that they come with these junction boxes, right? Because you really want to be able to mount them flat onto a surface. So you have these junction boxes on top of them. And so you lose area there, right? Especially if you look at something like the SunPower one, you lose all that area to your efficiency. We in the Solar Car Challenge calculate our efficiency based off the module and not the cell, right? So this one piece would be a module, and you have areas that don't produce, so your module efficiency is less, right? And so you got to consider that. There are things you can do. For example, you can actually cut that apart and then mount that junction box below through some soldering, right? And then you could then create holes for that junction box to sit in so that you don't lose that area. You can also see if you can cut panels in half or things like that to see if you can fit more stuff. So there are options that you can do, but the downside, yes, is certainly some of the loss production area. The next level, so we're going from the simplest to more complex. There are companies that either have a set of pre-made or a set of, you can actually order custom panels of a particular size. In our race, quite a few teams end up using SBM Solar as a particular vendor for that. SunPower could also do some things like that, and there's a contact about encapsulating panels there. And so we do have, and you heard yesterday, the sources and parts presentation has some references to what you can use. Finally, you could build your own, right? We talked a little bit about that yesterday in terms of acquiring raw solar cells and then laying it out, wiring them together, basically soldering each piece together, and then encapsulating them yourself. It's a very difficult process, so it's something you don't really want to do for your first year project. But once you get a rhythm, once you have tools to put in a jig and get a process going, it's not too difficult. It's just that you have to account for both the time and the cost in terms of you just plan for some breakage, right? You buy more cells than you need, knowing that as you construct your array, there will be breakage. But the thing about this is it's going to be very light because you can design your panels to be whatever material that you want to be. Okay? So I will call out that there are other companies that if you want to reach out to them like Suncat Solar, they can do this for you, right? You can say, I want a panel with these cells in this shape, and they can encapsulate these for you. The problem with that is while you don't have to go through the heartache of the time of putting a panel together, it's also very expensive. So these are options for laminated cells that really were made by other people in Suncat Solar. And doing it yourself, this is St. Thomas Academy putting together their own array. And so they've created a jig to wire these solar cells together. I'll say that I'll have a picture later on, but we no longer need to do this whole tinning of the cells from bottom to top, so it's a little bit simpler. But if you look here, there's quite a bit of irregularity throughout their array because when you make something custom, you're not going to get that level of reliability there. And so you can see that if you make a mistake, you're basically breaking it apart and starting over. It is quite a bit of effort. Now, what's neat is SunPower has made it a bit easier to build your own array. In the past, in the picture that you saw a couple slides ago, you see that there's a tab that goes on top of their cell, and then it actually goes underneath the cell, and then you have a straight line there, and you'd have to solder that whole thing together. SunPower has since changed their design such that the top of the cell has nothing but the solar cell collector. And all the connections, you have the positive end on one side, the negative end on the other side, and they have this tabbing that you can buy that essentially puts those together. So it is definitely a possible thing to do. I wouldn't say no one should build their own array, but tabs, it's a bit easier to put together. You could put a jig together to make sure that the distances between the cells are all appropriate, but your cells are still fragile, and so you will still have to plan for breakage there. So that's sort of the overview of solar arrays, from buying rooftop ones all the way to make your own. Once you have your solar array, how do you get that energy from that solar array into usable energy for your solar car? And the key technology here is our maximum point power trackers. So maximum point power trackers is essentially a way to convert your array voltage into your battery voltage. You can't just connect your solar array to the batteries, right? Even if you have a solar array that is slightly higher in voltage than your batteries, because your battery voltage changes based off of your state of charge, you really want some component in there to track your battery voltage and essentially provide array output just above the battery voltage so that you can maximize the current that you're driving into your solar cell, into your batteries from the solar cells. So that's what a maximum point power tracker does. Additionally, it does provide a level of protection that you wouldn't have if you directly connected. Solar cells are essentially collectors, and they'll convert solar energy into useful electrical current. But if you're dark, if you're shaded, you can actually get some amount of reverse flow. And so you might actually drain your battery via your solar cells, right? So power trackers provide that level of protection as well. So ultimately, what do power trackers do? They adjust the amount of voltage and current that you drive into your batteries to power your vehicle. So like I said, you can track the battery voltage of your state of charge and provide that level of voltage. If you understand how power works, power is simply just current multiplied by voltage. If you have a constant power and you lower your voltage, you have increased current. And current's really what you want to drive into your batteries, right? And so your power trackers can track that battery state of charge and provide the relevant current into your batteries. They're also a great source of telemetry. We talked about telemetry earlier in the session. And most power trackers have some type of tap that allows you to track the array voltage, array current, your output voltage and output current. So some of the choices that you can have for that, AERL is essentially started with a student that built a car for the World Solar Challenge, and so the AERL power trackers are very custom to solar car racing. They're actually called the Race Max, right? They're meant for that. And if you were to have any system voltage that's over 72, that's almost the option that you have. You really need AERL power trackers. There are other power trackers available out there. The Numera one is very small. You can see a coin compared to their power tracker. And then a lot of teams, especially in the classic division, like these grid-type MPPTs. That's the black ones on your screen right there. And they have a display for you. They're very reliable. And so we suggest that for starting teams. There are other ones as well. There's a Jenison one that's much smaller. And then you might be tempted to say, well, all I want to do is to convert your array voltage to your system voltage. So let me just put in a DC to DC power converter. Don't do that, because you don't get the advantage of a power tracker that can optimize the power that you get into your batteries. So DC-DC converters are really just like constant conversion. And so they're static in terms of what voltage that you are trying to convert to. I'll say this, we do have a set of 5 AERL power trackers that are sitting on the table over there. We're essentially trying to give it out to teams, so it ends up being first come, first serve for whoever wants that power tracker. So that's AERL power trackers. Okay, so the AERL power tracker, you can take a look at it. The AERL power tracker, and let me just go back real quick. The power tracker, what it's trying to do is to maximize the amount of power that you get in your system. And so this is a typical IV curve for a solar panel. You'll see that over the course of voltage, it stays fairly current, and then it hits this knee and it drops down. What a maximum point power tracker is to maximize what we call the knee here, to say, if you multiply your current and your voltage, this location where it starts dropping off is where you get the most power. And so the benefits of a maximum point power tracker is they will track via electronics how to get that point. Okay, so let's, from your solar array, you now go through this power conversion to your power trackers. Now let's talk about batteries. As with all decisions in our Solar Car Challenge, choose carefully. There's a lot of considerations that you have to make, and so you have to choose correctly for your application. So the things you have to consider is like, what voltage does your car run at, right? If you have higher voltage and the same amount of power that you're trying to get, that means you have lower current. What does that mean? It means that if you run at a higher voltage and lower current, all your cabling, the wires that you use for propulsion can be thinner. But yet, higher voltage means you've got, some components are limited, right, in terms of what you can use. Usually, teams determine their system voltage by their motor selection, right? The motor runs at a particular voltage at the optimal level, and so you would essentially match your system voltage with your motor voltage. You have to consider how much weight you can carry and how much energy you can carry at that weight. I'll say this, you may not necessarily want to run at your maximum capacity, right? Because if you decide to get your maximum capacity, but you don't have the ability to fully charge your batteries, then you're just carrying dead weight, right? So it's something you have to consider. It's like, how much energy can you use? How much can you recharge? Your consideration for a road race and a track race may be different, right? A track race is more of a continuous draw at a very known, well-controlled current level. Your road race, you're going to be braking for lights and traffic and then moving forward. So you get a very uneven current. So we require that your batteries be no more than 5.25 kilowatt hours. And for lead acid batteries, we measure that at the 20-hour discharge rate. And the way you look at that is most batteries advertise themselves as, I'm a nominal voltage of, let's say, 12 volts, and they're a 84 amp hour battery. So you just sort of multiply all those together. You've got 4 12-volt batteries, so that's 48 volts. 84 amp hours gets you 4,000 watt hours. So we do look at the nominal voltage, knowing that when you actually measure your battery voltage, it would be higher than, in this case, 12 volts. Peukert's number is something you have to consider if you have lead-acid batteries, right? The way it works is we advertise, and the capacity is done at a 20-hour discharge rate. So let's say 84 amp hours at a 20-hour discharge rate says you can discharge 4.2 amps over the course of 20 hours. Well, lead-acid battery chemistry is such that if you were to discharge, let's say, at 10 hours instead of 20 hours, it is not a linear conversion. You don't get, you know, 16.8 amps at 10 hours. You get less because the faster that you discharge, the less capacity that you have. And so when you research batteries, you have to look and see not just what your capacity is, but what the discharge curve is. You don't have to actually look at the Peukert's number. There's an equation for that. But look at this graph and say, you want the number, or you want your discharge graph to be closer to the red line than you do the other colors. Now, what's nice now is in the last few years, we have allowed for lithium iron phosphate to be used in all our divisions. So in the past, lithium-based chemistries, including lithium iron phosphate, was restricted to the advanced division. Now we allow it to be in all divisions. And so the benefit to that in terms of chemistry is it's really a Peukert's number of 1. There's not that much of that drop-off over the discharge rate. So we don't even talk about capacity at a 20-hour discharge rate. They don't advertise that anymore. They really advertise it at a 1C rate. But the real benefit to lithium iron phosphate is its weight, right? You get the same power for essentially a third of the weight of your of a lead acid battery. The caution, though, is we do require you to have a battery management system at the essentially series cell level. You have to track you have to have protections so that your voltages don't go out of whack, and primarily for over temperature and over current situations. And so if you choose to use lithium iron phosphate as part of the application registration information, we ask, as you say, I'm using lithium iron phosphate, here's the data sheet for my batteries, and here's my battery management system I plan to use for that battery system, okay? I will say that some manufacturers of the batteries actually incorporate battery management into each of the batteries, so you could submit that as an option, or you can have an external one. What's neat about lithium iron phosphate is a very, very stable chemistry, and so this is why we let it on all the divisions. And just for clarity, lithium iron phosphate, compared to some other lithium chemistries, do not require a Class D fire extinguisher. It's really a Class ABC or a CO2 fire extinguisher, so it's basically a drop-in replacement for lead-acid batteries. So let's say you selected your battery chemistry from lead-acid to lithium iron phosphate to maybe lithium ion or things like that in the advanced division. That's not the end-all be-all. Batteries are chemistry, and it's not one battery is the same as another battery. You'll have specs. Those specs are advertised specs, but they're not the performing. They don't reflect the performance of the battery. And so what you really want to do is once you acquire the batteries, go and test each one of them, characterize them. In this picture, you'll see St. Thomas Academy just rig up a set of light bulbs and essentially drain and recharge and drain and recharge their batteries so that they can determine how much capacity is truly in their battery. So they go and record over the course of time the voltage and the current, and then that'll help you get the amp hours that you have for each battery. Chris has a comment on that.
One of the things that I managed to learn, because I have a trailer that I replaced some lead-acid batteries with some lithium iron phosphate batteries to run Starlink satellite connection when I camp, because who wants to camp without the internet? One of the valuable lessons I learned is that a lot of these batteries are marketed as a 12-volt replacement when you talk lithium iron phosphate. But if you do the research on the materials, that lithium iron phosphate battery is not charged at 12.5 volts or 13 volts where a lead acid would be fully charged. They're actually closer to 14, or slightly above 14 if you want to achieve full capacity. I'm only mentioning this because if you're running lithium iron phosphate, don't assume the same chargers you might have had for lead acid are going to be able to top off those batteries so you get the full capacity out of them. Because I guarantee you, you'll only get about 60%, 70% of the capacity if you try and charge it to just 12 or 13 volts. So that's on you guys to figure out. But yeah, be aware. Those batteries run slightly higher than 12 volts, even though they're marketed as a drop-in replacement for a 12-volt lead-acid battery.
Thanks, Chris. So when we talk about batteries, some of the team favorites that we have from the classic division for lead-acid batteries are the Concord Sun Extender series and the Enersys Odyssey Marine series. Because lithium iron phosphate is a fairly new thing that we have in our race, we have no particular recommendations or selections from other teams with regard to that battery chemistry. Okay, so now we've gotten the energy from the sun into your car and actually stored in the batteries. Now, how do we convert that into actual miles on the road and laps in the track? So your motor selection, you have a few options. You have brushed electric motors. Those electric motors are the most inexpensive, but they're also the lowest in terms of efficiency. So it's always a trade-off in terms of, in this case, cost versus performance. You could get better ones of brushless ones, but it's a little more complicated, not too complicated. I think it's fairly straightforward for teams to incorporate. And we'll talk about some examples. An example is a Briggs & Stratton E-Tech. I think it might be advertised as something else now. A Lynch ML220, LM200, Perm Motor PMG 132 are very popular examples. These are what we call pancake motors because they reflect a sort of large and thin. And when I talk about efficiency in these cases, you know, when we talk about low efficiency, we're talking about 90% efficient. So, you know, it's still fairly efficient. The brushless just gets significantly better. A Mount Energy ME0909 is a very, very popular selection in our race for motors. And they are fairly lightweight compared to our much older, you know, advanced DC motor designs, fairly cost efficient, and they do allow for a range of system voltages, although it doesn't go up beyond 48, right? So a lot of teams like to use like a 72 volt system. You wouldn't be able to use this motor for that application. So when you look at the ME0909, or for any motor selection, what you really want to look at is your motor efficiency curves. Every motor has an ideal operating range, and that ideal operating range affects the efficiency of power conversion. You'll see, I believe, the efficiency is in blue. So this line that goes up and then down reflects the efficiency, and it reflects the efficiency mostly at a particular RPM. So if you want to get the most efficient use of your motor, you certainly don't want to be down in this level and running at, 4,000 RPM or below, because your efficiency drops, way low here, right? And you really don't want to be running up here because you start getting diminishing returns here. And so you really want to be operating at a range where you have your highest efficiency there. Why do I mention that? When we get to gearing, and when we talk about how you gear, you keep that in mind in terms of looking at your motor documentation and knowing the best efficiency, and you want to make sure that stays within that range. Very old example is an advanced DC motor. I would imagine that most teams wouldn't be using these anymore. It's much heavier, much older. This type of motor is what I used back in 1997. You might be able to get something like this because you got it from another car, but certainly no solar car teams that participate today use something like that. So other options is MEO 907. And then sort of from the brushed to the brushless to hub motors are a lot more efficient, because when you think about brushed or brushless motors, you're talking about adding a sprocket on the drive and then running it to your driving wheel via a chain or a belt. And there's some losses of efficiency there. Whereas a hub motor is essentially in the hub of your driving wheel. And so you don't have that conversion loss in efficiency. There's two hub motors that we know. Actually, there's really three. I haven't updated this chart yet. There is an NGM in-hub motor that has been in use by college teams and some of our high school teams probably like 8 years ago or earlier. Some models of them are still around and still are very, very efficient. And so if you have that, that's certainly an option. Most teams nowadays, if you're looking for a very, very efficient hub motor, you go to Mitsuba. Nomura is the US distributor of the Mitsuba motor. We're talking about 25K or more in terms of getting that motor and controller combination. But it's very efficient. It's an option for your more advanced cars. And anyone who uses an in-hub motor would be classified as an advanced division car. Before we get there, there is another in-hub motor. I think it's GS motor or something like that, that comes from China. That's another option for an in-hub motor that's a lot more inexpensive than this. And so we had some teams actually use that motor. And I would recommend that if you're interested in in-hub motors, to go take a look at the team specs for previous cars in the advanced division. You'll see their entire car's data, including what motor they selected, and you can then look up the data sheet for that. Okay, so you have a motor, but the motor is nothing without its controller, because the controller is really the control for how much current is provided to the motor. It affects your speed. You essentially have your accelerator pedal attached to your motor controller, and that will drive how much current that you provide the motor. One very common one that we see for a lot of vehicles is this Alltrax AXE. It's basically a two-phase, in terms of a positive and negative. It's very easy to wire. You have essentially a common negative, and then you have your battery connection, and then you have your motor connection. So those are the three big spades that are there. And then there's controls, and this is where you put a 0 to 5K foot operated potentiometer, and that'll control how much you want to drive your motor. What's really cool about an Alltrax AXE motor controller is what's hidden behind this black rubber grommet. Behind there is an RS-232 connection, and that allows you to hook up some software to it and actually program it. I have seen teams use that programming to smooth out the curve of acceleration. You can, via this, have a potentiometer that goes full throttle, and you can actually program this controller to not let it go sharp full throttle. You can actually let it smoothly come up to that maximum level, and then the same thing going down. So it's really cool, and for those who are interested in electrical engineering, you can really play around with that. If you're looking at brushless motors and you're talking about three-phase motors, you need to get something like a Sevcon or like a Kelly controller that you have essentially your battery inputs, positive and negative, and then you have three outputs to your motor, rather than this just positive and negative. So that's your motor selection there. So now let's talk about gearing. Yes, question. Right, yeah, so that's an important point. You can't just arbitrarily choose what motor controller to put on your car. It really needs to be matched to your motor. So especially with regard to, like in-hub motors have quite a matching. Even some brushless motors require a certain controller to go with it. So when you buy your motor, you typically buy the motor and controller together, and so that they integrate well together. But ultimately, you'll see that if you're talking about brushed motors, they usually come in just these positive, negative, and so you could probably use Alltrax or other things. It's not as tied in. And then when you start getting the three-phase brushless motors, there might be more of a matching set. And so wherever you buy your motors, they'll probably say, and this controller does well with this motor. So good point. Any other questions with regard to actually arrays, power trackers, batteries, and motors? Okay, let's talk about gearing. We build these solar cars, and especially if you haven't driven a solar car before, you will say, hey, yeah, I'll probably want to go, 50 miles per hour, 40 miles per hour on the track all day. Well, I would suggest you take a look at our race data and race results over the course of the last few years. You'll know that the average speed, not cruising speed, of the winning solar cars in the classic divisions might be something on the order of, low to mid 20 miles per hour. And so if you gear your car to go, 50 miles per hour, and you end up driving it at 25 miles per hour, what happens? Happens that you end up driving your motor in less efficient range in your RPM, right? If you gear it and say, hey, I'm going to run in my optimal range for a 50 mile per hour speed, you cut that in half, your RPM cuts in half, and now you could be out of your efficient range. So be careful about what you expect, right? Be more conservative. Say you're going to run more like 30 miles per hour or something like that max, and then go out and test. Collect the data on your car's performance based on its weight, based on its rolling resistance, based on its aerodynamics. You'll know how much current you get using to drive at a particular speed. And then if you're able to test that, maybe then you could optimize your gearing ratio to increase your speed if you can run faster, or lower your speed if you don't have enough energy. So be careful. You'll see that a lot of times in terms of the efficiency of motors, you'll end up getting a fairly small sprocket on the drive side, something on the order of like 10 to 12 gears on your teeth on your gear, on your sprocket. And then your drive, your wheel side of that would be something on the order of like, 70 to even, I've seen 108, 120. So, and then you could just calculate based off of your diameter of the tire, your circumference essentially, and your gear ratio, what your maximum speed is. So here's the calculation, right? You can calculate based off your you have to convert miles per hour into revolutions per minute, and then you can take a look at the ratio between your sprocket and your tire and its circumference, and that'll tell you what your maximum speed is. So there are some vendors that you could use to get some of these sprockets. Okay, let's talk about the rest of the electrical system. We talked primarily on the main or propulsion system. Let's talk about the rest of the system. We call your main battery, your motor and controller, your array, all that is part of the propulsion system. And one of the key things there is to choose the correct gauge wire for the job. And we'll talk about wiring in a sec. We'll also talk about disconnect switches and fuses, and then we'll talk about the auxiliary system. So we talked a bit about electrical schematics yesterday. We have seen in the past electrical schematics drawn out on paper. We don't allow that anymore. But really, we're wanting to see something closer to the thing on the right. And you'll remember when Brian talked about electrical diagrams, he talked about two things. He talked about schematics, and he talked about wiring diagrams. Both are useful. We want to see an electrical schematic that will be able to tell us how your components are connected together, essentially the logic of your electrical design. We do not require, but it will be very, very useful to you to also have a wiring diagram that shows you physically how you manifest your electrical schematic into your solar car. And that way, if you need to find a wire, you say, hey, where's the wire that goes, from your battery to the switch to your power trackers, physically where they exist in your car. That would be a wiring diagram. We ask that you submit the electrical schematics to us during registration so that we can review it for you. Okay, so as part of the electrical stuff, we have switches and fuses. So in the past, we required you to have a push-pull switch that would disconnect your entire electrical load from your batteries to the motor and from the array to the batteries. We have now required in the last few years you to use relays to do that disconnection. And so ultimately, a lot of teams used to be using these big red buttons that had these big lugs to be able to disconnect the full current. You don't need that anymore. You can buy much lower duty switches that can then operate a relay that'll do that disconnection for you. So we expect that these switches will be slightly smaller. You can certainly get the same big head, but you don't need to have that amount of big copper that's right there. We do, as part of this, also allow for push twist on instead of like push pull, and we'll talk about that in the rules section. Definitely make sure that you take a look at the rules, and we'll talk through it with regard to how relays work. We do another thing, focus on the fuses. A lot of teams end up buying fuses, and they simply look at how many amps and how many volts is this fuse rated for. But a lot of times, fuses are rated for volts AC instead of volts DC. And it's much easier to break a circuit if it's AC because the electrical current essentially passes through zero each time as it goes through the sine wave. So you'll see that any fuse that is DC rated will be beefier than those that are AC rated. And so make sure when you're looking for fuses that you look for a fuse that's rated for DC for the volts that you are operating at and at the appropriate current draw. Okay, we do require also a low voltage indicator for your supplemental battery system. The supplemental battery system allows you to essentially run your lights, your horn, and essentially anything that's not used to drive the solar car. Well, as part of that, because it runs so many things, we do require that you have a low voltage indicator to be able to warn the driver when that supplemental battery is getting low so that you can change it out and then charge it in your garage bay or in your support vehicle. And so one option that you can use is something like this, where you have that audible alarm you see in the corner here for a low voltage. Okay, wiring. This is one of the key things that we see a lot in cars, is that teams don't use the appropriate wire for the currents that they are using, okay? Most teams should be using something like a welding cable and a 4-gauge welding cable as their propulsion wiring. Now, that's a generalization. You really need to look at how much current do you expect to be running in your motor and controller system, and then or what you're getting from the solar array, and then size it accordingly. So you'll want to make sure that you look at these wiring tables that will tell you, this is the current that it supports over a particular distance, right? One of the things is that if you are carrying current for a longer distance, you'll need more conductor in there so that you don't lose that energy. So that's one of the key things to be aware of. Another thing is the connector. So just because you have like the right size wire, if you don't have the appropriate lugs and appropriate connectors for that wire, and that is not properly crimped down and soldered down, you'll have a chance to lose your connection. And we talked about that in the soldering workshop, right? Beware of counterfeit cables. Some cables do advertise themselves to a particular rating, but you really ought to test it out. But the key thing is to be sure to size your wiring to your system. One of the things that's not on this chart that I also want to make you aware of is the difference between solid connectors and stranded connectors, or a solid wire versus stranded wire. We see some teams come and get wires that are solid connector or solid conductor wires, and they're really, really rigid, and they're efficient in energy transfer, But then we start seeing them sort of put bends in it, and it really weakens the structure of the wire. And so if you end up having to bend that wire a few times, it could very easily break, whereas stranded wires are more forgiving in that respect, and I would certainly recommend that you look at stranded wire instead of solid wire for that. Okay. We talked a bit about heat shrink yesterday in the soldering workshop, but we really require that you insulate your connectors, and we'll be checking for that in scrutineering. And so even if we didn't, it's just better to heat shrink, not just for safety purposes, but it provides just an additional physical, structure to help get your crimp connectors all secured in there. And so you'll definitely want to consider using heat shrink as well. And then finally, I'm not going to brief this chart, but the soldering tools, you all got an experience to use those. But here are some considerations for you about the type of soldering tools that you would use, the type of solder that you would use, and things like that. But these are critical things that you'll need to construct your vehicle. Okay, so that's all I have in terms of the electrical portions of it.